Section 3.9 talks about derivatives of exponential and logarithmic functions. So it turns out if you have an exponential function, and recall what an exponential function is, it is a number raised to a variable where that number base, we call it the base, say a, is bigger than 0 and not equal to 1. So if the base is bigger than 0 and not equal to 1, then the derivative of an exponential is the exponential times natural log of the base. So if I had y equal 3 to the x, the derivative will be 3 to the x, which is the exponential, times the natural log of the base. And it turns out a special case is the natural exponential, which is the exponential with the base of e. If you take a derivative, that is e to the x times natural log of the base, which is e, but that's a 1. So it turns out to be simply e to the x, and it's right there. And of course, don't forget the chain rule. If y equal e to the u, and I take a derivative, well, you get the exponential back times du dx, assuming you're taking a derivative with respect to x. So, looking at the first example we have, if I would like to take a derivative of f to the negative x divided by x, well, that would be the quotient rule. I'm going to get the denominator squared. It's going to be derivative of the top. Derivative of the top is e to the negative x times negative 1 by the chain rule, times the denominator, minus the top times derivative of the denominator, which is 1. And that's the calculus. You want to clean that up. You could factor negative e to the negative x out. Out of the first, I'll have an x, and out of the second, I'll have a plus 1 over x squared. So the answer with the back of the book will be simplified, and it would look just like this. And again, the rule of thumb is if you start the problem with a negative power, you could leave the answer with a negative power. Second problem I have would be f of x equals a square root. We know how to take a derivative of a square root. We agreed you're going to memorize that. 1 over twice the radical, whatever that is, by the chain rule times the derivative of the inside. Derivative of e to the 2x is e to the 2x times derivative of 2x, which is 2, plus, and the derivative of 2x is simply 2. Now again, that's the calculus. You want to clean this up. You could factor a 2 out of the top. You'll have e to the 2x plus 1. And the 2's cancel out, and there's my answer. Now, a good question would be, when do we apply the chain rule? You apply the chain rule on every single derivative you will ever take. You will never take a derivative and not apply the chain rule. It applies everywhere. Now, natural log of 10 is a constant. So when I want to take a derivative, I'll ignore that because we ignore the constants, take a derivative of the function, and multiply the results. What's the derivative of 10 to the x? Well, again, it's right there. Derivative of a number raised to a variable, an exponential, is the exponential times natural log of the base. And those, of course, cancel each other. And it turns out to be simply 10 to the x. All right. Now, we'd like to look at the following problem. Derivative of an exponential, like we said, that is the exponential, times, if the base is not an e, natural log of the base. By the chain rule, since that's not an x, I have to multiply this by the derivative of sine of 3x, which is derivative of sine is the cosine of 3x. By the chain rule, derivative of 3x is a 3. There it is. Now, let's talk about derivative of logs. That's a bit more fun. Derivative of natural log of x is simply 1 over x. which means if I want to take the derivative, which means if I wanted to take the derivative of natural log of u, that would be 1 over u du dx, again by the chain rule. So if it's not an x, I have to apply the chain rule. If this was natural log of x, I would have said 1 over x. The fact you don't have an x there, when you take a derivative of natural log, we call this argument of the argument, that's 1 over the argument. If the argument is not an x, you have to multiply by the derivative of that, which is, and there it is. And if I want to take a derivative of 342, I see the product rule. Derivative of the first would be 2x times natural log of 9x plus x squared. The derivative of natural log is 1 divided by whatever you take in the log of, which is the argument, by the chain rule times the derivative of the 9x, which is a 9. And of course that cleans up, and that would be 2x natural log of 9x plus, and the x cancel one of those, simply x. So we should simplify our answers to match the back of the book. Now we get to the next problem. When we're dealing with a log where the base of the log is not an e, well, we could use the change of base formula, and that's pretty much a good way of getting around this. I'm going to do this problem 2 different ways. This will be natural log of 6x to the 4th plus 3 to the 5th divided by natural log of 7. Recall that log of a number is a constant, so when I take a derivative, 1 over natural log of 7 is a constant. We ignore that. We're going to take a derivative of that log and multiply the result by 1 over, oh boy, natural log of 7. Now, the derivative of a log is 1 divided by the argument times the derivative of this. Well, this has a power function. You bring the power down, subtract 1 from the power, times the derivative of the inside, which is 24x cubed. Now you notice a lot of cancellation there, meaning you notice I can cancel those 4 with one of those, and I could say that is 5 times 24, 120x cubed divided by natural log of 7 times 6x to the 4th plus 3. Now I want to show you how useful logs could be. I could have taken that problem and altered it slightly, not altered it really. I could have used properties of logs to simplify that a bit, and let me show you what that means. So I could have said, by properties of logs, f of x equals, I can take that 5 and move it up front. Logs are the only functions that we use to bring powers down, and I could say this is 5 times natural log of 6x to the 4th plus 3 divided by natural log of 7. And when I want to take a derivative, I could say 5 divided by natural log of 7 is a constant. Derivative of a log is 1 over the argument times the derivative of the argument, which is And as you see, this looks a lot simpler than this. And of course, the answer would be the same. That would be 5 times 20. Let me clean that up just a bit. 5 times 24 is 120x cubed divided by natural log of 7 times 6x to the 4th plus 3. Similarly, I wanted to show you something really quick. Did you notice up there we had natural log of 9x and the 9's cancelled out? There's a reason for that. If y equal natural log of 9x, if I take a derivative, that's 1 over 9x times 9, and that turns out to be 1 over x. The reason for that, I could have written this as natural log of 9 plus natural log of x, one of the properties of logs. And then when I take a derivative, derivative of a constant is 0, derivative of natural log of x is 1 over x. So that happens all the time. Logs allow you to manipulate very complex functions and differentiate them a lot simpler. All right. Now we get to the last portion of this section, and that deals with something that we do not know how to take a derivative of. So let me make sure we are clear on this part. If I told you that we're dealing with a power function, so if I told you y equal x to the a, if I say what's the derivative, you say bring the power down, subtract 1 from the power. That's if you have a power function. A power function is when you have a variable, x is varying, raised to a constant. The power is fixed. And if I told you y equal the reverse, an exponential, the base is fixed, but the power is varying, then you say y prime is a to the x times natural log of a. We know that as well. But do you notice on these problems, the base is varying and the power is varying, which means none of what we did works. So here, it doesn't match this and it doesn't match this. Now, whenever you're dealing with a problem and there's a power involved and you can't seem to get around it, most likely logs are the key. What I'm going to do, I'm going to log both sides of the equation, which is mathematically fine. So I'm going to take natural log of the left, natural log of the right. By the third property of logs, if you recall, I can take that power and move it and make it multiplication. And if I differentiate now, if I take a derivative with respect to x of both sides, the left side, derivative of a log is 1 over the argument times derivative of the argument, which is y prime. Here, do you see now I'm dealing with the product rule? Derivative of the first is 1 over twice radical x times the second, plus the first derivative of natural log of x is 1 over x. And all what I have to do is cross multiply and x to the 1/2 and x to the 1, this cancels 1/2 of those. So you're really looking at this. And all what I have to do is replace y by what it equals. And this will always look like that, even though I put that back. But I was able to take a derivative of this relation, even though I couldn't take a derivative initially. And the reason I'm not saying a function, because we're not sure if it is a function or not. And the same deal happens on 348. I noticed that this is varying and this is varying. We have no rule for that. So what I'll do, I'll take the natural log of both sides. The natural log of the left, that's a y. The natural log of the right, well, notice the right has natural log of x raised to the natural log of x. I know that's too many logs. Property of logs, the third property, I could move that up front. And now that becomes multiplication. Instead of power, now these are multiplied. When I say take a derivative, you'll say, all right, well, derivative of the left, 1 over y, y prime. The product rule. Derivative of the first is 1 over x times the second plus the first. Now, derivative of the second is going to be a bit messy, just a bit. Derivative of a log is 1 divided by the argument times derivative of the inside, which is 1 over x. Again, I know these are too many logs, but if I cross multiply, I'm looking at natural log of x over x, and here those cancel out, plus 1 over x. And if I replace y by what it equaled initially, pretty much I'm done. And that's the trick. Oh, they both have the same denominator. So I could say, and what was y initially? Y was natural log of x raised to the natural log of x. And that'll be my answer. All right, a couple more before I conclude this section. And here they are. Again, we have a problem. The base is varying. That's not constant, and that's not constant. So what I'm going to do, I'm going to log both sides. And properties of logs, I could move that up front. And now when I take a derivative, that will be 1 over y, y prime. Product rule, derivative of the first times the second plus the first times derivative of the second is 1 over the argument times the derivative of the argument, which is 2x. And if I cross multiply, and all what I have to do is put that mess back there, and we're all happy. X squared minus 1 to the natural log of x, and that will be my answer. Now, one thing that logs allow you to do, I am aware that you know how to take a derivative of this, you would use the quotient rule. But observe what happened if you log both sides. If I take natural log of the left and natural log of the right, I'm going to say natural log of y equal. Now, we know that log of the quotient is the difference of logs, and I'm going to write that as a power of 1/3, and I'm going to move this up front. So I'm looking at natural log of y equal natural log of x plus 11 minus 1/3 natural log of x squared minus 4. Instead of using the quotient rule, I could simply say 1 over y, y prime, that's taking the derivative. Derivative of natural log is 1 over the argument times derivative of x plus 11, that's a 1, minus 1/3 is a constant. Derivative of a natural log is 1 over x squared minus 4 times the derivative of the argument, which is 2x. And if I cross multiply, pretty much I'm done. So what was y? Because when I multiply, I'll get y. Here I'll get 1 over x plus 11 minus 2x over 3 into x squared minus 4. And remember, when I multiply by y, y was initially x plus 11 divided by the cube root of x squared minus 4. Of course, if I distribute that in some cancellation will happen, but that's pretty much it about this section.